dimensionality if you do this in these models. One of the things I'm arguing to people who are deep learning people is that they sort of say, oh, but with a deep Gaussian process you introduce this. You can get rid of this if you like, but it's stupid to do so. Because if you get rid of this, you're actually turning your model back into a Gaussian process. I'll try and give you the intuition. I've said this many, many times. Some people are now realizing you can prove it and make a very complex looking paper, but it's kind of obvious. Because what happens if I keep this matrix, if I keep this as K1 dimensionality and keep this as K2 dimensionality, and I'm going to say each of these layers is a Gaussian process, then the dimensionality of K1 and K2 goes to infinity. If I don't introduce this bottleneck, the dimensionality of the equivalent mapping matrix, and using clever Gaussian processes tricks, you can do all that, also goes to infinity. And as you increase all of this to infinity, everything stays Gaussian. So if you can do this, and people like keep rediscovering it, I think it's kind of uninteresting, but they get very excited about it. You can do this by just putting a kernel of kernels. So if you think of the covariance function, the covariance functions always have an inner product in them, right? Typically. If you kernelize that inner product, like turn it into another covariance function inside it, you are building the model where you don't bottleneck and you take these layers to infinity, where each of these covariance functions is in a different layer. The first person to point this out was, I think, Lawrence Saul. Quite a nice paper, not from this context, and it keeps on surfacing again and again. But why don't I find that interesting? Because of what Mackay said. Because if you go back to being a Gaussian process again, you've done a lot of work. You've got highly parameterized covariance function, which is interesting, perhaps, but there's lots of different ways of doing that. And I'm not sure you've overcome the basic complaint that David has in that statement, right? So what we're going to try and do here, these bottleneck layers, this dimensionality of Q, will render the thing non-Gaussian. So what you have now is this sort of system where we've got these intermediate variables Z. And I've introduced, well, you've got U and V instead. So we'll see that, here the input's coming in X, and there's just a linear mapping to the first intermediate variable Z. And then after that, we don't actually tend to put this in, but well, you could. There's nothing to stop you. Then you sort of going with this matrix U, and then mapping to H via, that's the sort of bottleneck layer, right, coming in. So you could implement this as a neural network in TensorFlow or whatever else. Now, the reason that that's sort of I like that is if you look at this object here, the mapping from, say, H1 to Z2, sorry, Z1 to Z2. If you look at these, if we look at these mappings between layers, what you're seeing is a classical basis function model of the type that people are using quite a lot in statistics, where your basis functions are just the activation functions in here. It's a vector valued model because it's not one-dimensional output. It's multi-dimensional output. Now, the reason why you can do all the maths when you take these layers to infinity is the same reason if you look at Chris Williams' old papers on infinite neural networks, because as you take expectations down here, things become only dependent on the statistics of each of these intermediate layers. As these intermediate layers become narrower, the samples from the Gaussian process become less concentrated around the standard deviation. As they go larger, the samples from the Gaussian process become highly concentrated on the standard deviation, such that interpoint distances between samples from across the layers just come out as a point function, which is why all these expectations then become tractable, and the whole deep neural network you can resolve tractably. But that concentration around the mean, around the standard deviation, is the thing that you don't want to happen. Because as that happens, everything becomes Gaussian again. And when you keep these layers small, you don't have that concentration. So I'm going to show you some plots of that, and some people have talked about the consequences of that. But the idea then is, so each of those are either a basis function model, or if you're with a classical ML audience, you have to tell them, look, each of these is a single layer neural network, because they don't know what a basis function model is. And we can replace each neural network with a Gaussian process, and you just get now this thing. So you're saying, well, instead of having this very constructive with a load of parameters, I'm just going to go back to the non-parametric approach, which I think is the right way to think about these things. To me, it's fine to do deep neural networks and everything else when you're pragmatically trying to do something, but I think that you should be thinking about your function even in the deep neural network case. The problem, of course, with the deep neural network is the nature of the functions that you're considering is very, very difficult to describe mathematically, and that's why Gaussian processes are very, very interesting, because it's much easier to describe them. Okay, how am I doing? So sometimes when I talk about deep learning, I like to show the Callista-Flockhart detector, which Facebook spent a lot of money developing. And I think that they're running this on every face that goes into the network. So this is the sort of thing. Now, there's some nice work by the people at Prowler around how you can do these convolutional layers, right? And I think one area, and I think that's a very interesting area. Personally, I've utterly tried to avoid applying Gaussian processes to images because I've been through this sort of stuff before. When when an algorithm's working well in a real space, if you want to demonstrate the quality of another algorithm, going and competing in the space that they're already dominant is probably not the best idea. It's kind of like turning up at I don't know, Juventus and saying, yeah, I play winger just like Ronaldo, so pick me. No, don't. Just tell them and say, I play central defense or goalkeeper or something. You don't try and, the reason they're so successful is because they work well on images. And I think there's a really interesting open question about what sort of inductive biases these convolutional layers are bringing in. We know that they're trying to bring in translation invariance, but there's a lot of interesting work around what other things they're doing to the covariance function. And of course, people have now built covariance functions that allow you to do these convolutions in Gaussian processes and show that they perform as well as, better, I believe, than deep neural networks. But I'm not really going to worry so much about that. What we're really worrying about is these fully connected layers at the end. And actually, it seems to me the jury's still out as to whether just connecting multiple fully connected layers works that much better than just doing a GP. Certainly for small data, for large data, maybe it seems to work, and why it works. So you can get a lot of insight into that from Gaussian process. This is when I explain deep learning to people, I say it's like pinball. I say, look, you've got a ball at the top, one-dimensional input, and we're going to use this because I'm going to show you some what I call pinball plots later. So your input is at the top, so this is an old pinball machine with just like regularly laid out pins. So your input X is here, Z1 is here, Z2 is here. So it's 1 to 1 to 1. You have to think in high dimensions. And then in this case, it's classification. Output is Y is being split at some threshold to yes or no. And then a data point comes in, and the location of these is like the basis functions. So you move them around to try and get the ball. This is one has been incorrectly labeled because it was green, so it should be no. Because this is at initialization. And then when I say to sort of, okay, so what happens next? This is how I do my public understanding lectures of deep learning. I say, so next, after training, we move these pins around such that the ball goes to the right place. Now, I kind of like this model just for myself. It's funny, I often do public understanding things to explain something, and then afterwards I kind of think about the analogy a bit. So what's going on in a Gaussian process here? Well, actually you've got one layer only, normally, but we're going to do deep. And what's going on is the pins are stochastic, right? So what goes wrong with this setup? Well, we saw that in like when AlphaGo played Lee Sedol at some point. And actually, I'd met Demis like a couple of weeks before, and we'd asked him whether he thought it was going to win. He said it should win unless Lee Sedol manages to play the neural network, I guess the recognition network, but who knows, into some zone that it's never seen data before, right? So, and he said that Fan Hui, who was the European champion who they had employed, was constantly playing AlphaGo to try and get it into regimes it had never seen before, so that once they've got there, they can play out, right? So you only have to go there once, and then they can simulate away from that and understand all the futures from that board position. But until you've been there once, the network has no understanding of that area. And that's like a little bit like no one's ever dropped a ball into the pinball machine from this side. Now, that's in a one-dimensional case. Even in a one-dimensional case, you can see you need quite a lot of balls to be confident about the pass through this machine. As you go high-dimensional, you're playing pinball in hyperspace, and these basis functions are sort of somehow planes, hyperplanes, moving things around. And so you can see in these deep neural networks, what kind of goes wrong is where you go into an area of parameter space where you've never been before, then the ball just goes random places. And as that space becomes very, very high dimensional, well, I actually one of my constant irritations in the community at the moment is, oh, and it's surprising that we can move the vector of input a little bit of distance and the cow is classified as a car. Well, it's not surprising if you've thought about high-dimensional spaces at all or understood things from this perspective. It's utterly unsurprising because what you're doing is you're basically, in this sort of system, you're finding a small movement of the ball to take the ball into a place. These are very, very high-dimensional spaces where no data has ever been before and no data ever will be unless someone pushes you down there. And you can find whatever path you like through this very, very high-dimensional system, right? In 1D, it's less surprising. So those adversarial examples I find unsurprising, but it is not surprising that Gaussian processes are more robust to that type of thing, because in regions where the ball has never been, you just have full uncertainty of where these basis functions are, inequivalent. You have full uncertainty of what the path should be. So you end up spreading across all values and your uncertainty goes up. That's why we love Gaussian processes, because of the uncertainty. I mean, we don't love them because of how difficult it is to just fit them to large data sets. But mathematically, what we're sort of saying now is that we're building a composite multivariate function. And of course, if you show mathematicians this, they say, well, what are you doing? This is all a waste of time. That's just a function. But the reason you're doing this is because you're, both in neural networks and Gaussian processes, you're taking components and combining them together in such a way that the end result is something that's much more complex. And in neural networks, what they're really driving forward with that is things like the structure of the inputs, translation invariance, that type of thing. I think the strength that's coming from deep Gaussian processes is almost orthogonal to that. I mean, that's my belief, my intuition. I don't. You guys can see if you believe the same thing. Now, this is actually equivalent to a Markov chain probabilistically. So when we're doing it probabilistically, that's something. Don't forget that, right? So this whole thing is just a funky Markov chain where each of these things is being defined by a Gaussian process. Now that's nice because we can also then go back to the world of graphical models. This is just the simplest form of graphical model. And with a deep Gaussian process, you can start doing any kind of structuring or building of the model you like. You can attempt to learn the structure because you can use all the probabilistic tricks. And that seems to work well in the cases we've tried it. So I often think the sort of things, probably talked about that. Oh, I'll come back to that. Let me just check. We checked everything. Oh, yes. So why deep? So Gaussian processes give priors over functions. And one of their really nice properties is that the derivatives of the process, because that's a linear operator on the process, is also a Gaussian process. But that's also immediately tells you something about the type of functions you can represent. You can only represent functions where marginally at any point the derivatives must be Gaussian because they're jointly Gaussian. And that means that you can't have step functions in your function. They don't like that. They hate that. Because that's not marginally a Gaussian derivative. That's very heavy-tailed. If we look at so we're trying to model a very simple thing like this. The derivative here is 0, 0, 0 heavy-tail. That would be like, worse than Cauchy, infinite derivative, either 0 or infinite. So they hate that. And actually, Levy processes are all about bringing jump processes in to Gaussian processes. And in fact, well, a pure mathematician or a probabilist wouldn't say that, but I see them as that. A Levy process covers the area of Gaussian process, and jump processes, which do allow this type of behavior, are interesting for that reason, but difficult to work with because they don't exist in closed form. Now, for particular covariance functions, these models are universal approximators, but what you can see is that that's the sort of result that we liked back in the 1990s and caused us to adopt deep learning. But that's not good enough, because what happens, they're universal approximators. With enough data, they'll approximate any function. But that has to be so much data that it's in a regime that you're utterly uninterested in. And not only that, I think it was Philip Hennig has shown some wonderful plots of how badly they converge towards those functions, even with very, very large data, what nasty things they can do. So these derivatives might ring alarm bells because they don't believe in the jumps, as well as what David was talking about. So I'd say what's going on, if I'm speaking to statisticians and probabilistic people, I think that what we're doing with deep Gaussian processes is actually a sort of broader trick, which is just stochastic process composition, combining stochastic processes together to change the class of processes you're working on. And if you see, once once you realize you're combining in this way, if each of these stochastic processes, which is effectively giving me a function, is a unit in itself that I can compute with, it's possible that I can design approximations, even though it's unlikely if I've created an interesting stochastic process through doing this, it's unlikely to be available in closed form, but there may be various approximations like sampling or variational inference I can use. And I think that that's a general approach that we've seen for deep Gaussian processes and not yet seen applied anywhere else. So maybe it's not a general approach, who knows. But this is the sort of thing I'm also interested in. You rarely see this. And why not? So this is a sort of deep model where you're taking an observation off the side. And it's kind of obvious you can do this with a deep Gaussian process. You can also, in a deep Gaussian process, learn the structure of where this observation, so these are two data sets. You could simultaneously learn where these data sets should sit on the structure. That's something that I think certainly not published on. I think people in my group have played with at times, but that to me has always been a key thing. So why do I find this important? Imagine if this layer of the deep Gaussian process was some latent representation of disease that you were interested in. Yeah, this might be survival. So this observation might be sort of taken off the sort of what's in the physician's brain about when they take all this information about the patient and then they sort of make a survival prediction, but it's a very abstract prediction relative to the details of the information. Information coming in, which could be anywhere around here, but at the moment happens to be here, but multiple sources of information would be at sort of more detail. So this might be the result of, this might be the sort of clinical notes, this might be the result of a scan, or even in a crazy world where there's all sorts of extra stuff going on here, it might be the image of the scan, which is related in some very unusual way to what the physician thinks. So the ability to do that and to structure learn in those models has always seemed to me critical. And I've been talking about models that look like that for, I think, 10 years. And it's sort of interesting how rarely they come up in the deep neural network world. They sometimes come up. But of course, the problem is as we do these nonlinear functions, we're having to propagate probability through the nonlinearity. So the very advantage we're getting is also sort of killing us. So, I mean, we can sometimes, so the GTM, which was one of the first, well, actually, I suppose latent density networks, which was from Mackay, was one of the first approaches to do this. Of course, people are doing variational autoencoders and all sorts now, push uncertainty through models. They were using like points, either sampling or grid-based points to do that. And those were things, again, that were going on. I was imprinted with those in Aston in 1996, which is why I keep working on them, because I think it's my idea parent or something. So the nice thing is, even in one dimension, with this sort of nonlinearity, you can get very complex non-parametric distributions. In fact, when we do deep Gaussian processes for unsupervised learning, one realization you have is a Gaussian prior isn't very good, right? I said, whenever you look at, that's always an interesting trick to do. Whenever you look at the result of a variational autoencoder or any of these deep stack models, right, and then they show the latent representation in the top layer, over which they're typically putting a Gaussian prior. One observation is it will never look Gaussian distributed. Now that's odd because they put a Gaussian prior over it, right? If the model was fitted correctly, it would be a Gaussian distribution in that space. The reason you don't see a Gaussian distribution in that space is because if you decompose the likelihood to get the latent distribution correct somehow, it's only one term in the likelihood which is dominated by the data, right? So there's n terms in the data. If you think of PCA as saying the same thing, right? PCA is saying Gaussian prior, linear output, right? You never see unless it's Gaussian data, you're never going to see a Gaussian in the latent space because you're effectively doing linear projections of the data. Unless that data is Gaussian, you won't see Gaussian. So we're very used to it in these latent variable models. But it's wrong, and it's an indicator of model mismatch. It's an indicator that your model isn't powerful enough to represent what it's doing, and the way it's dealing with that is in the latent space, putting data in a non-Gaussian way. And that's, I've never actually, it's come close with some deep GP models to see somewhat of a Gaussian distribution. But even with deep GPs, we don't really see a Gaussian distribution in the latent space. So one of my thoughts on what's going on, or we think about when we are doing unsupervised learning, is the first layer is just giving you a non-parametric prior over the latent space, which is the sort of thing you really want. You don't want a Gaussian prior because there's often be clusters, like these could be different digits or something, and you want to see those clusters. So a Gaussian prior is going to tell you, no, everything's clustered together. The reason they don't do that is because the latent variable isn't that strong a term in the likelihood, so the data tends to dominate, and you do tend to see clusters. But it's kind of wrong to see clusters. It's an odd thought. But this is difficult to sort of fit these things. So what's going on? So what happens in a deep Gaussian process is we only have to solve one of these integrations, it turns out. Because as we look at, say, let's just look at this. Each of these layers can be dealt with independently. And what we've got going on, if we project back to a Gaussian at each of these stages, so if we choose to sort of approximate what's going on here, which will be non-Gaussian with a Gaussian, then we only have to push a Gaussian through here. And that's the trick we use in deep Gaussian processes, that at each layer, Gaussian goes into, well, in this case it's input, but this is a Gaussian process. So this is a Gaussian output going into a Gaussian process. The output of that is non-Gaussian, unless that's a linear Gaussian process, right? Or it's Gaussian in the region where things are linear. So what we do is one of the approximation approaches is to project back to Gaussians. And a very common way of doing that is variational methods. So when you are in that situation, you look at any layer. This is the bit of maths you need to solve, where you've got, this is now my Gaussian process of z going out. So my input here is z, my output is y. And I've got a posterior approximation which is the variational approximation, which I'm assuming is Gaussian. And I need to compute this expectation. This other expectation, the prior in this case is the prior coming from the Gaussian process above. So this is Gaussian, this is Gaussian. This is clean, because it's just the covariance between two full covariance Gaussians. Of course, for large data, there may be issues on that, but in fact, it turns out that we diagonalize this one. So this one's all right, but this term is a problem because it's the expectation of a Gaussian process under a Gaussian input. The mathematical tricks we used for the first one. Okay, so let's just look at this. You've seen this multiple times now, I'm sure. This is the likelihood of the Gaussian process. And I kind of hide z when I do these likelihoods. So I've just reminded you under here that z, which is the input to the Gaussian process, is in the covariance function. And in a rather nasty way, it's in the covariance function in a nonlinear way. And then you're taking an inverse or a determinant. So that really, really messes things up when you're trying to compute the expectations of these terms under Q of z. So this is the log of P of y given z. So the variational approximation requires you to take that expectation. So we need to take this expectation under z, but of something that's nonlinear inside an inverse. So this is the sort of obstacle for doing these things. If, by the way, you're doing a linear model, Bayesian linear regression, the form of this is XX or ZZ transpose. And actually, it turns out that you can do this expectation. And that's variational Bayesian PCA, which my supervisor, Chris Bishop, did, and I implemented. OK, so what we do instead, and did you do have you done the variational approximation to GPs? So I wasn't here yesterday, I had to be in London. But yeah, so what you do, so one of the ways we present those approximations is in this way, which we think of as the collapsed variational bound. So that the likelihood, I've actually fully dropped z now, so this is just the likelihood of the Gaussian processes, is lower bounded by something of this form, where this is the prior over the inducing variables, and this is this sort of lower bounded effective likelihood that comes from applying the variational approximation to the likelihoods part. So this is something you've seen before. This is how we do variational large-scale Gaussian processes. But normally, well, OK, so if you do stochastic variational inference, in this case, you keep this form and you do variational inference on this form with a Q of u, et cetera, et cetera. But normally what we now do is we collapse that. We do this integral turns out to be tractable because the expectation of f is only linearly dependent on u because of the setup of the Gaussian process. But in this case, we're not going to exploit that. So the dependency on u is through this expectation, which I've now clarified here, is over f given u, which is the sort of inducing variable locations, and z, which is the inputs, not the inducing inputs. I know people use Z for the inducing inputs. We're not using them here. It's the actual inputs here. And what the trick is to sort of, what we want to be able to do, so that I've reintroduced the conditioning on Z, is this integral. And the trick is, don't collapse that integral. Don't do that integral. It's an easy one to do. So your temptation, quick, I can do that. No, don't. Because if you don't do that one, you can actually do this integral under Z. So this is a lower bound, and the variational approximation, we've already got a variational approximation. Now we're going to do a lower bound on the expectation of this lower bound under the prior over the inputs. And that turns out to be something we can do if we do the integral over P of Z first. Well, when I say we're going to do the integral, we're doing it variationally. If we do a variational integral over P of Z, we don't collapse P of U. We choose to do a variational integral over P of Z. So we sort of pretend P of U doesn't exist now, and we look at this object. Then we can do a further lower bound on that. And that's at the heart of the variational approximation to Gaussian processes. So that is lower bounded by this thing here. Ci, by the way, is, I've included it here. If you don't, obviously, if I take that out, then this thing is actually a probability distribution, and a probability distribution cannot be bounded by another probability distribution unless they're the same thing. I mean, it can't be less than or equal to, because they're integrating both to 1. So you'll notice this Ci in the variational lower bound, I've unlogged it. Normally you see it in logged form, so you see the trace term. This Ci is the exponentiation of the trace term, and it's actually ensuring that this is a lower bound. If all the diagonals of that trace term are 0, then this is one of the beautiful things about that variational bound. It's unique to it. If all the diagonals of that trace term are 0, then this is just a product of 1s, and you know you've recovered truth. Very unusual as a variational bound to know when you've uncovered truth. But in general, the trace term is non-zero, and that's there as well. But we apply the variational lower bound to that, so we're taking this thing, which is a standard Bayesian integral that we wanted to do, but we're just lower bounding it again and introducing Q of Z. So Q of Z being the posterior approximation, which we're going to force to be Gaussian. Normally we assume it's spherical. We have done some work where we assume it's non-spherical, and it got rejected, and we never published again. Actually, that work, in that case, we assumed Q of Z was a Gaussian process. So we actually invented a variant of variational autoencoders, but it was rejected. But we were trying to do it for a different reason. It turned out by doing that, by assuming Q of Z was a Gaussian process over Z, with the inputs being Y and the process being over Z, it was a way of meaning that we could assume this wasn't diagonal, which is something we wanted to do, but the model didn't like it. It switched off the non-diagonal terms. So we gave up a bit on that. So, and then this form here is what this looks like. You're looking at this log. Sorry, that should be a Z. You're looking at this logarithm here, and you need the expectation of that, which fundamentally means you need these two expectations. So if you look in the code where we do this sort of thing, these are often called the psi statistics. And these expectations are of the covariance function between the inducing variables and the output function under Q of Z, where Q of Z, again, is not the inducing variable inputs. It's the inputs for F, which is important when you look at this one. Because what's gone on here, and this is the low rank approximation, the rather nice thing that happens is this expectation is tractable because Z does not appear in this inverse. Right? These things don't invert. They're non-linear, but they don't invert. And for certain covariance functions, you can compute these expectations analytically. In other cases, and I think it's in Andreas's thesis that you can do it by sampling, but also Hugh Salimbeni and Mark Deisenroth. No, was it them? No, actually, that's the wrong Salimbeni paper. I think Hugh Salimbeni and James Hensman and others. No, I can't remember who did what. You know, your brain goes at some point. But Salimbeni was definitely the first author on doubly stochastic deep GPs, where you actually approximate these through sampling and do stochastic variational inference. Now, there are other approaches to doing this. So the first thing, my first attempt at deep GPs was actually 2007, but we didn't call things deep then, so I called it the hierarchical GPLVM, because that's what we used to say, hierarchical. Why didn't that catch on? I don't know what went wrong. They also call it that in statistics. These are effectively hierarchical models in statistics. So I did a map approach because I couldn't push the uncertainty through. And the interest, actually, this is there's some really odd stuff in that paper. The map approach works because at the point, I didn't allow any, so in general deep GPs, we allow a general covariance function at each of these layers, right? So you can actually have white noise, and it's actually very useful to have white noise being injected at each of these layers. I didn't allow that for the map approach. So the odd thing was, the outputs of each layer was a deterministic delta function. So at the points where there is data, the map approach was somehow valid. It's only when you move away from the data. So this, as long as you didn't put the noise in, it worked really well. If you put noise in, it just blew it apart. And it was, the thing I wanted to do in that paper was learn the structure, and we just couldn't do that. It wasn't until this work that we could start learning structures, and work with Carl Henrik and others has shown how beautifully you can learn those structures. Hamiltonian Monte Carlo approach was last year's NeurIPS. That sounds interesting. I don't quite know the details of how they've done it. The reason it's difficult in general to do Hamiltonian Monte Carlo in these systems is because the correlations are so strong between different layers that the samples often mix even quite slowly. But this team seems to have worked it out. I've not really checked the details. And Tang Bui and others have proposed an expectation propagation approach to dealing with those. I should probably I don't know when I pause and ask for questions, but I should have probably done it ages ago. And you're all like, what's he on about now? So let me just stop there for a moment and see if there are any questions about like the ideas. I've certainly been through the maths too quickly. The reason I kind of do that is because it's in papers, and I'm only putting it in to show that it's not just waving hands and intuitions, which is the bit I do like. But at some point, you have to do some interesting maths to get the results out. And by the way, this result, the thing about this result is I was at Manchester with Michalis, who was working with me when he developed the variational sparse approximation. We were actually working on Monte Carlo methods for GPs, and I told him to look at these low rank methods, and he came back and says, oh, well, look, this variational method is that you can do it variationally, and this is much better. And I'm like, oh, yeah, so it is. And then the next thing he sort of said to me is, oh, you know that we can integrate out the latent variables. And I'm like, oh, can we? Because he was the one that spotted that you could flip this inverse. And I think that to me is fascinating, because I'd been staring at these equations for ages, and I'd never seen just that simple thing, that if you don't collapse that, you can do that integration. And that turns out to be critical. So questions, anything at that point? No?
So to the adversarial community, people who work on innovations and improvements to adversarial defenses and adversarial attacks, never-ending stuff in high-dimensional space, what would you could say one thing to them? What would you say?
I think you have to be very careful about deciding other people are doing the wrong thing, but I tend to do it all the time. So I think it's good, fundamentally. Well, actually, what goes on in that adversarial community now that's going on, and we can talk about it in terms of these models. It's super interesting, highly technical, very fascinating stuff. When they are doing this type of model, they're basically faced with the same problem we're faced with. I don't know what the right, somewhere around here, right? So what they try and do is they say, I'm going to define an L1 norm or some kind of norm in the input space, and I'm going to say I'm going to be robust to that. And adversarial training, not the training where you're against an adversary, where you're trying to be robust to it, they put in bounds, and then what they have to do at the next layer, it's like putting a Gaussian through these layers. It comes out as non-Gaussian. They get the same problem. They put a sort of box around the data point, and at the next layer, I think that you're often looking for like a convex hull of where the point could be, but in order to understand it at the next layer, they have to draw a box around the box that's come out of the previous layer. You see what I mean? Because they have to do worst case, and we're doing average case. And I think that you just see this pattern again and again and again. When we're projecting back onto a Gaussian, we're somehow doing average case. We're not really sort of saying, what's the worst that could happen? Someone could have moved it into that point, so we have to take that point and push it forward. So they have a very, very difficult job of going through each of these layers, carrying that box. I think that they do some amazing mathematical gymnastics, and some of my favorite people are working in that space doing some very, very cool things. And I think the problem is utterly irrelevant, because I just don't think anyone is going to attack your neural network in that way. Because the truth of what's going to happen is if it is an image attack, it's going to be some sort of patch or something put on the image, which is not going to be well represented by a L1 norm. It's going to be some sort of strong correlation in a particular direction where a number of pixels have all gone there together. And if you want to consider all of those, your task is hopeless. So another way of thinking about it, now it doesn't mean they should stop, right? If you are working on it, don't stop. Because actually, what tends to happen with these things is people just doing a bunch of math for some reason, and then something cool pops out, right? As long as they stay sane and keep talking to the rest of the community. But I just don't think that that's irrelevant. Everyone says, oh, look at this thing, a camel is detected as a pig. Isn't that terrible? We must prevent this happening. And it's sort of like, you can see why people get into that and why the general public think that's interesting. I just think it's not the type of attack we're going to actually have, and that the type of attack we're going to have is going to be far worse, and it's going to involve complex systems. And my favorite example, which I sometimes show when I talk about this, is my 10-year-old attacking AI systems, because he's a very sophisticated intelligence relative to them, and there's nothing, I mean, he's now 12, but about to be 13. But particularly when he was 10, there's nothing that amused him more than making an AI system look stupid. And we kind of forget about that. Like, my mum is always very kind to AI systems. But 10-year-olds aren't. And those attacks are just crazily well different from that. So I think it's sort of mathematically interesting and largely irrelevant in its current form. But I also, when you look at the history of things, interesting things people were doing in the community that we sustained over time, they often led to something else. So, and I'd say that if you do want to be practical about it and introduce some robustness, why worry about the worst case? Because you're already not worrying about the worst case. Just do average case analysis and be properly probabilistic, and that will defend probably as much as you can get for the moment. Because what you'll get out of a probably probabilistic approach, if you've done it right, is when you see this totally bizarre input, which where someone's moved across millions of dimensions, pixels a little bit amount, the probabilistic approach, ideally, I think we probably wouldn't be there yet with deep GPs, but would be better than deep neural networks. The probabilistic approach, ideally, would say, I've never seen a data point like this before. I'm super uncertain about what the output is. And then you're done, right? So I just, I think it's cool. Sometimes you listen to talks. The maths is really hard. And it's great to have lots of hard maths in the community because it gets really good mathematicians in. And when you've got some simple maths, you can ask them and they tell you the answer quickly. After asking you for ages why you want to know that. Yeah. Other questions? It's an interesting question because
Have people tried using the uncentered transform to push the Gaussians with its nonlinear network?
Yeah, no, that's an interesting idea. I don't want to say no because I think it gets quite close to the way I view things, which is almost everything's the same at the end of the day. I think probably the closest to that would be, of course, I said that these are Markov chains. And if you look at models like recurrent deep Gaussian processes, you've got the same thing going on. You have a Markov chain across time and then across depth. And if you look at work on the state space area, from particularly the Cambridge group. Oh, and the guy's name escapes me for the moment. He was working with Carl. They were doing a lot on state space models. And I'm pretty certain they would have tried the uncentered transform. And if you look at that mathematically, it's the same thing. Of course, where you're deploying it may be slightly different, so the dimensionality of some of these spaces may be different. But I think they got that working. I don't know if they used it in Pilco, is it? Yeah. Yeah, precisely. Yeah. Well, when you think about that, that's kind of what this is. I mean, for me, like it's all graphical models, right? That's what this is sort of saying. That's now an HMM in structure. I'm not using it in time, but once you've got once you've got the component that you can stick these things together as you like, which you do have with deep GPs if you're pushing back to Gaussians, you can basically build anything you like. I mean, whether you can compute it on a large data set is the difficulty. Yeah. So that looks a bit like an HMM if I keep putting an observation on. Of course, in those models, they would tend to assume each of these transitions is the same, right, across time, because that's how you make them infinite in time. And in the deep GP, you would rarely do that. So there's this odd thing going on at the moment. There's a lot of interesting analysis around deep GPs, almost all of which assumes that you use the same covariance function at each step or the same dimensionality of each layer. I've never, I mean, apart from when I'm sampling them to show stuff, I don't know why you would want to constrain it like that, other than to make the maths of the analytics of the thing easier. But with HMMs, of course, you do that because you're moving across time. So you can't invent a new GP to move across time every time time moves forward. Other questions?
If you're looking at images, well, what is the proper assumption for the marginal distribution of the inputs? Because usually you do that to pixels. Well, I cannot imagine it.
So yeah, that only comes up if you're looking at images with missing values. If which is something that you might do. And that is a difficulty thing, a difficult thing. If the image is an input, typically we're conditioning on it, so we don't care so much. But you're right, sometimes we have modeled images outputs. And yeah, I mean, that's one difficulty. I think we tend to just say, well, let's just assume it's Gaussian, and that kind of works. Why does that work? Because most image outputs are pretty low noise, actually. So, you know, it probably doesn't matter what distribution assumption you have. The assumption of your distribution form only matters if you've got higher noise. Other questions?
Somewhere in the middle of the doc, you mentioned something about Gaussian process methods being competitive with convolutional neural nets for face processing, or
for images, yeah.
Recognition or something.
On ImageNet, I think.
Like the recent results using the neural tangent kernel or something entirely different.
I'm referring to where's Nicola? Is he here? He'd remember. Who's on that paper with James and the convolutional Gaussian processes? Mark van der Wilt, yeah. Mark van der Wilt, and it's lots of clever tricks. It's like building covariance functions which are convolutional that allow translation invariance, and then it's using inducing variables in clever ways to make them tractable. Stop me if I'm getting any of this wrong. And then it's a follow-up. Their first paper, I think they didn't quite get to the ImageNet result, but then they realized that they had a very strong translation invariance from the way they'd constructed the covariance. So they used more covariance function construction techniques to ensure that the translation invariance was only being locally valid in any region, which makes sense on an image. Images aren't really totally translation invariant. And then my understanding is, and this is talking about papers in coffee shops, not reading them. It's way easier. With the authors. And my understanding is that then they outperform ImageNet standard. I don't know, some neural nets on ImageNet. Is that right? You would know it better than me. You're in coffee shops more with them than I am. Yeah, so not the other. It's a translation invariant case. It's a real convolution, actually. It's a sort of. That's right. Yeah. So you can nail mark on that. Yeah. So Neil said. Other questions? It's a lot of hard work. It's very good work as well. The thing I worry about with these things, because we had this experience when Gaussian processes, 1996, so it's a long time ago. And the competitive technique of the time was not neural networks. We could kick their ass on any problem that we were looking at in those days. It was support vector machines. And we spent a lot of time trying to persuade people you needed uncertainty and everything else to do support vector machines. And no one really paid any attention. I did this paper which is called the IVM, which to me was the demonstrator that you could do as well with a Gaussian process on the MNIST data set, which was still a big benchmark, considered large then, as a support vector machine was doing. And so I finally achieved that and slightly outperformed SVMs or whatever, and learned the covariance parameters and all these things, and just no one cared. The reason no one cares is because, well, so what? You've got all this algorithmic complexity and years of work versus I can just run my SVM. and it's already sort of dominated. So it's actually very, very hard to supplant a method. Of course, the reason you might want to do it is for things like adversarial examples, and I get very, very cross with people. And I think I may have said this to James, I can't remember, but we can say it to Mark. It's why on earth would you go to all that effort and then not check adversarial examples at the end, right? And this is one thing that I find super frustrating in the community at the moment, is there are reasons to do things, but a lot of the time people don't seem to follow them. So you read the whole paper and you're just like, well, you could do that, but why would you do that? And in that case, the biggest reason I can see why you would do that everyone's excited about, even though I don't care about adversarial examples, is adversarial examples. And I would be fascinated. And maybe they've done that since. I think that they said, oh, we didn't have time or something. But to me, the paper's like got a massive hole in it without the adversarial example check at the end. Still an amazing paper, I should say. Okay, so why am I so obsessed with uncertainty? And I don't know. One of the things that science is sometimes faith-based, and one of the faiths I have is that somehow it's a good idea not to throw away the uncertainty when you're stacking these things together and to worry about it like it's a precious thing and have to do all this mathematical work, versus the alternative, which is now the mainstream approach in this area, which is to throw it all away and try and retrofit it. And I don't know which is right or wrong. I'm just doing the thing that I do, and I've done it long enough, probably can't do anything else. But I'm very, very encouraged by how rubbish the results are for Bayesian neural networks, and yet they're state of the art. And this is a very recent paper, which I find, it makes my skin crawl when you look at their error bars. And for reasons that they're not even looking at, I think, because people keep doing this. They keep publishing crazy error bars. Unfortunately, this is a bit, maybe you can't quite see it. Let's see if I can zoom in on some of the horrors. It's a very good paper. You get to do this if people aren't using your methods and they're using other people's. If you're the dominant method. Oh, is that actually zooming? No, it didn't really zoom, did it? Okay, so this is actually the classic. I haven't even checked these methods too much. This is the classic thing that if you do a neural network uncertainty, this is in my thesis actually. This is how I found out about how bad uncertainties are on neural networks, because that's what I was doing, Bayesian neural networks with variational methods. And I don't know this method, but this would be classic what happens if you use variational inference with mean field over the parameters, and you assume independence in that posterior of W. We're assuming some independence on those latent variables, but because the Gaussian process is correlating everything back together, we still get lots of correlation between these error bars. And what happens, and this is really hard to break away from, I did mixtures of mean field in my thesis to try and break away from it. It's super hard to do this. Actually, the error bars where the data is are very nicely calibrated. The mean is going through where the data is. I'm sorry, it's hard to see. If you want to check, you can check the slides online. And this is just taken directly out of their paper. And the sort of one standard deviation of error is very nicely around the data. Now that has to be, in my mind, the very first criterion for a method that is saying it's got error bars. That in the regions that you actually have data, that the mean you are estimating should closely estimate the mean of the data in some smooth sense, and that the standard deviations should cover the 95% confidence intervals. Now, what fascinates me is they are so desperate to show that they can do this, which a GP does naturally, which is as you go outside regimes of data, you begin to gain some uncertainty in what's going on, that they have ignored the fact that their error bars around the data are crap. I mean, this one, the mean, starts failing to go through the actual interpolation here. Here, and this is very, I mean, these aren't the exact pure results, but you can see the tweeted result from this paper. You have mean functions that do not go through the mean of the data anymore, and error bars that do not give you, they are wider than the standard deviation of the data. And people are excited because they're getting some effects like this. These effects are a nightmare to achieve. Why are they a nightmare to achieve? When they come from correlated regions, so in the regions of these hyperspaces of parameters, there's these sort of narrow ridges where you can wander down that ridge, and as you're wandering down that ridge, you're moving all these basis functions in such a way that the mean does not change. The mean must not change because it's strongly constrained by the data. But these tails move around. And you find all those spaces, they're these ridges, which are very, very flat, but they're in specific directions. And in a deep neural network, they'll bend around and do all sorts of funky things. And the only way you recover this, which basically you don't recover in a fixed basis function model anyway, so you only recover this if you're using a very, very large deep neural network, is if you wander down those regions. Now, they are in this paper wandering down those regions, right? They are trying to come up with ways of wandering down those regions. But they're doing it at the expense of killing their mean function and their standard deviation. And the fact that people will proudly state they've done it, I think this is one of their main results where that happens, proudly state that they've done that and they've started to get error functions that in the regions of uncertainty, really totally reassures me that probably, for the moment, until the thousands of people who are doing it this way discover something that they haven't seen before, that the Gaussian process is really a great approach to doing this. And I don't rule it out that it will come one day, but let's not hail its arrival. Let's not hail the Messiah when it's just Brian. That's the GP result, right? This isn't my work. I haven't fitted this. I haven't done anything. It goes tightly through. Look at the error bars around these things here. I mean, some of these are just demonstrating, but that's the GP result. I think one of these is their result, and you can see the tweet from the team. It's so far ahead. I mean, genuinely, if you are in the regime, it's a depressing thing. I would love it if there were a model that were doing things like this. And the reason this happens is twofold. One, the GP is non-parametric in terms of its basis function layout. So everywhere you want a basis function to be, there is one magically because there's infinite of them, right? That's a property of the sort of, if you're using a non-degenerate covariance function. Of course, you can use degenerate because you could make a neural network. So that's one of the things that's going on. But the other thing is going right back to that statement from David Mackay. Is like, oh, well, in the infinite limit, we're losing these correlations between these output units. What is going on? Right? And it is a weird thing, and it's kind of surprising, and are we missing something? Maybe. But the result is we can integrate along that ridge, because in our case, that ridge is a Gaussian. Right? So all those movements of things, we're taking in the whole probability distribution, which is what allows, I mean, these are surprisingly wide error bars, actually. They seem to have too narrow a covariance function. I would be a bit suspicious of those. I don't know what covariance function they use, which is what allows this thing. Every time you see someone producing a Bayesian neural network result and showing error bars like this outside the regime of data, be highly suspicious. The only approach that I've seen that does it really, really well is the one I was trying to compete with in my PhD thesis, which was hybrid Monte Carlo, or as we now call it, Hamiltonian Monte Carlo. And that was Radford Neal. And it was just kind of impossible to get anywhere close. So it is possible, but those posterior covariances are very, very complex, and you have to be very, very careful. So I'd just be very suspicious about them. I think the paper sounds very interesting. They're trying to use it, and maybe you could fix these things. But I just think that their heads are too turned by, and that's not their result. I think this is their result here. Their heads are too turned by their desire to have large error bars, which they're not getting down here, outside the regimes of the data. And they're not focusing enough. Actually, their interpolation, to me, doesn't seem good in the middle. And of course, that's still it's a meritorious way to go. Keep working at it. Maybe they'll get there. It's a faith-based thing for me that you sustain the uncertainty and you do what we're trying to do with deep GPs. But you have to have some sort of faith in science when results pan out over decades. Okay. So this is like, so actually you can do a deep Gaussian process with linear Gaussian processes, and this is the sort of thing you see, nothing exciting happens. Actually, the process, what happens as you do it is you get a, what's the distribution of, I've forgotten the name of the Wishart. You get sort of like, because you're putting a Gaussian over the covariance of a low rank component of a Gaussian, which is over the low rank component. So you're sort of, actually, I think that the distribution, this is a square, right? And I'm just doing a sort of linear Gaussian output sample, linear Gaussian output sample, linear Gaussian output sample. I think if you study what that effectively means is going on, is that you're increasing the degree of a Wishart sample over the covariance function. So this is a sort of, that becomes much sharper. It becomes less sort of broad like that. This is the thing I liked. This is what I always liked about UC. So this is sampling from a deep Gaussian process with 2 observations each layer. I should have been clearer about that, same as the previous one, but here it's non-linear. Now, the notion to me, and the reason I found this interesting, is back in the old days when Jeff was first pushing deep models, he was pushing the notion that you were able to include abstract features at the top of the network, and that those features then propagated down. Now, what's quite interesting, and this plot, I think I showed it at Cambridge, and I think David Duverneau was then inspired to do their pathologies of deep learning paper, because something particular is happening here that doesn't always happen. And I'm going to use this plot to explain why, if as I increase the layer width, everything returns to Gaussian. See what's happening here? This square is going projected to 2 dimensions. It's folded over on itself, right? Again, it's probably a bit too small, apologies. So it's got this feature now. You can never get rid of that feature, because in this 2-dimensional space, that fold over where that's come over to there is now in the same position. So that feature never disappears. And what's going on as you go down the network is more folds are recurring. So that continues to occur. Whatever you're doing in this space, it always happens. So this fold here you can still see there, and it's embedded in here. It gets lost because the whole thing's getting tangled up. Now, let's think about that. When do those folds happen? They happen in low dimensions. So I'm trying to give you the intuition about what the dimensionality of these latent spaces are occurring. If this was a 3-dimensional space, those folds would happen less, right? So you would tend not to get the case where you're getting it folding over. Probably the previous example was better for the fold. So this fold here is less likely to happen. Think about that. Why can we think about that? When you can do this for envisaging Gaussian distributions. I think that they're kind of odd to think about, because you show all the points of a Gaussian, and you sort of think, well, of course there's stuff near the mean. Every time you think about a Gaussian, there's always points near the mean, aren't there? You know, I can picture it in my head. But in high dimensions, what's going on? So it's like this. If I sort of had Gaussian samples, now we know that's a sample from a 2-dimensional Gaussian, and obviously there's points near the mean. So what's all this stuff about concentration around the standard deviation? Okay, but what if I tell you, actually, I'm just showing you a projected down version of a 3-dimensional Gaussian. Yeah? If I do that, are we doing time? Oh, cool. So if that's a 3-dimensional Gaussian, some of those points must be out of the plane. It's like looking at a tree, right? The actual space that the tree is taking in terms of the 3D space is sort of small. But as golfers know, if you hit a ball at them, the sort of 2D space projection is quite dense. Because in that projection, things have come down. So if I said, no, that's generally a 3-dimensional Gaussian, you now know that a number of those points that look like they're near the mean have been moved away. If I up, you realize, oh, if I'm looking at an infinite dimensional Gaussian, right, none of those points are near the mean. They're all tightly on a shell. They have to be. They all, because I've sampled so many times that the distance, you can show that the distance from the mean to those points, as you go to an infinite dimensional Gaussian, converges to a delta function around 1 standard deviation away. Now, I want you to do the same trick when you're looking at this. What if we hadn't projected this from a t? We obviously done it from a 2 here, but what if that was sticking out of the plane and there was another direction where we'd sampled it? It would be less likely to fold over on itself, right? And if we did that again to 4, 5, 6, 7, it would be less likely to fold over on itself. Until if we do it to an infinite dimensional Gaussian, it would never fold over on itself. And that folding over, that type of effect, turns out to be what drives the statistics of this thing to be non-Gaussian. So as I make these are the Z layers, remember? Because now we've got a sort of basis function model between each one. As I make those Z layers infinite, very, very high dimensional, you return to a Gaussian process with a new type of covariance function. So at each layer, how you choose to set that dimensionality is telling you how Gaussian things you want things to be. Of course, in practice, we learn that dimensionality using ARD priors. So we can actually learn the Gaussianity or non-Gaussianity of the system. OK, so that's actually, this is somehow I don't have network, but this is, these papers are saying, I like these papers a lot because I'm so excited when people are doing mathematical analysis of deep Gaussian processes, because I think that's one of their advantages. But as all papers perhaps claim a bit more generality than they have, I'd say that you would never build a deep Gaussian process model, probably. Well, I have never built a deep Gaussian process model in the way that either of these papers describes before they do their theoretical analysis. So you know, as with all theory, be very careful about the assumptions, but they are interesting. And this one in particular is showing that the derivative distribution of the process becomes more heavy-tailed. So they do a lovely theoretical analysis that says, under certain conditions, the derivative distribution of the process you are building becomes more heavy-tailed as the process goes deeper. And there we can see we're getting away from the Gaussian marginals. Okay, there's a video of some of that stuff. So this is one of my favorite data sets. It's marathon data. And I used it because when we do Data Science Africa, the first time we did it was in Uganda. And Stephen Kiprotich is only the second ever Ugandan gold medal winner, and he won in London, the marathon. So it's stolen from Girolamo and Rogers to look at sports data sets, but they look at sprinting. And we're in this for the long run, so we look at marathon instead. So this is a data set I use a lot because I find it interesting in this year here. I mean, it's a simple data set, obviously. But this year here, this was in, I think, St. Louis in the United States, and the marathon runners got lost. So my marathon time's about here, I think, something like this, a little bit slower than that. But they got lost that year, and so there's an outlier, which is nice. And it's also got other interesting characteristics, like they sort of across the wars, they stop running, and there's sort of larger noise, and then the noise changes over time. So I like it because of this other reason too, which actually, it's at one point no one knew, but I keep saying this, and people seem to know it now. This is a young gentleman called Alan Turing, and this is like a newspaper cutting that you can find online about his marathon time, which I can't quite read it here, but my memory says it's 2 hours 46 in 1946. That's how I remember it. There was no, the next Olympics is there, and he would have been about here. This is like 2.5 hours. So he was only 16 minutes out of winning. He was 10th in the UK championships. And at that time, UK was stronger in marathon than it is today. So I don't know you in this room, but my a priori bet is no one here has run a marathon faster than 2 hours 46. Has anyone here run a marathon faster than 2 hours 46? No. Yeah, and Tom is actually quite good at sport. I mean, a 3-hour marathon is like people's benchmark. 3 hour will get you into Boston, and that's what everyone's obsessed with, a 3-hour marathon. He's 14 minutes ahead of that. It's just extraordinary. So I think in some of the films about him, he jogs up, but he's like played by an actor that's a bit overweight, so you get no idea about how fast he actually was. So you can ask interesting questions about, that pace, I can't do that pace over 5K, not at the Sheffield Park run at any rate. Anyway, so the question is, would he have won the marathon in 46 had he run it? And so we're trying to now, that type of question, we want the probability distribution. What's the probability he would have won it? And this is a Gaussian process fit. And of course, the fit is compromised. I mean, there's lots of things we could do about this. You've heard about non-Gaussian likelihoods. We could do a heavy-tailed likelihood. We could do various things here. But just in this case, I've just used a standard Gaussian process. And you know, it's actually not too badly killed by that. You know, Gaussians can be quite nasty affected by outliers, but the variance is very, very large. I'm showing you the noise variance as well because it's trying to capture that on. The noise variance will always sort of be compromised by that. If you count, of course, this is probably quite well calibrated, right? Unlike those error bars we saw before, because 1 out of 20 points is outside the error bars, 5%. So it's happy-ish with that. But not a great model. Now, so can a deep Gaussian process help? And more interestingly, how does it help? So this is the deep Gaussian process fit. And it's not using any discontinuities or any of that powerful stuff I said. And this is one of the interesting things when you do these 1D examples that are easy to look at. Oh yeah, you can do that too. But there are cases. I mean, I don't really care about whether Alan could have won the marathon or not. And if I did, I would just start doing all sorts of heuristics, of course. But yes, I think when you're testing a method, you often don't do that because you're trying to say, well, imagine if people didn't know about 1904 or something like that. So a nice example, I used to do some work with Formula 1 teams, and one of the interesting things we looked at was how could you predict the sort of cutoff time for practices. They still do it and sometimes get it wrong. Like they do the qualification cutoff times. First, like I can't remember how many they take out, but they take out like 5 each time. And you need to be in the top 10 fastest. But they don't want to run more times than they have run in the past. So you're trying to do sort of, we did Gaussian process interesting regression things around predicting what the cutoff time would be. And in that case, we never deployed this because in practice we just did what you said. But it was actually quite hard to tell what the outliers were. And the outliers were, you know, because someone had pitted or because they get held up. And in that case, the nicest thing we did, which I just did with some students, and we never actually, because we'd finished the contract by then, but I still had the data. And it's a cool way of getting students who at the time were uninterested in machine learning to do machine learning. We did asymmetric likelihoods. So we did a sort of combination of a Gaussian and an Earth function, which you can do EP on. And it just worked beautifully because the Earth function worked out what the sort of speed that they were never going to go faster than, because that was their upper limit, and then it used the Gaussian for this massive tail. I just love techniques that are doing that automatically, because once you've done that, it saves so much handwork going through removing outliers. So if you can, it can be nice. In this case, I'm now also showing samples. They're probably a bit unclear because these error bars can be very misleading, as we'll see. The output of these processes is not Gaussian. So I'm showing you Gaussian error bars at 95 confidence intervals, but these processes aren't Gaussian. What you can see is it's decided that things were less certain in the early days and it's become more confident. But the interesting question is, how has it done that? So this is only two layers, two Gaussian process layers. And what you can see is the first thing it's done is it's actually taken the year, and then this is Z1, right? So mapping from year to Z1, it's actually broadly linear, apart from something it's doing up here. After about 1980, it's flattened off. So you can see how it's injecting uncertainty as well. There's quite a lot of noise here, right? So that flattening off is in this region here, where the function has become very flat, right? So although it's not really clean to your eye, this function is much flatter than a Gaussian process would want to do in this space. That is not the mean, bear in mind. Like a Gaussian process would return to the mean, but it's got this capability now to return to a location, it's decided, as the sort of saturating thing. Of course, this function itself is returning to the mean, right? So over time, that effect would disappear. The next layer is mapping from that and looks very broadly like the original function. Why? Obviously because that previous layer is pretty linear apart from this thing here. So this next layer, yes, all those later time points are being mapped into the same location. But now the variance on this process is much, much smaller. So the variance on the input is large. So you're moving around here. But in this flat region, because this is flat as well, the end variance is broadly going to be, I think, quite Gaussian and quite constant, right? Whereas it's also mapped, basically, by the way, you can see it's mapped that outlier back through. This will be the outlier here. It's mapped it there, and then it's effectively managed to sort of, this is the projection point of that on the input going out from there. So that's, sorry, it must be that one there, I guess. Yeah, it's that one. It's mapped that outlier there. It's pushed it back. So how does that now? Okay, why did I introduce pinball? Because I invented pinball plots. So in the pinball game we played before, you can see what's going on. You drop the ball in these places here. This is the input, the year. And then this is the pace. It's decreasing over time. If I had it increasing, this would be harder to see. So in these plots, when things are linear, they're sort of just straight vertical lines. But what's happening is it's not quite linear. It's mapping all these points to a point here, and then it's mapping all those points down. With uncertainty each time. I'm showing you the uncertainty here as a sort of Gaussian random walk. So the idea is that the ball is moving with uncertainty through the pinball machine. The points are not the pins. The points are just where the mean function of the ball arrives at the layer, and then you project it down. So that's sort of a simple data set. This is a different data set that I used with that I used to show. I would have shown it had I given one of the introduction talks. Here we were trying to use Gaussian processes to understand, is this noise or is it signal? It's a gene expression data set. And it was a very simple technique of fit a Gaussian process and see if it wants to use signal, what the signal to noise ratio of the resulting fit is. And I used this particular example because it's an example where it's from this paper. It's an example where the likelihood of this fit, which is minus 16.6, so try and remember that, minus 16.6, that's some signal but large noise. Regular Gaussian process, not a deep Gaussian process. This is minus 18.4, so no signal, all noise. Noise being Gaussian. Of course, if we change the noise model, different result. But this is saying that it's all noise, so it's actually not as likely as the signal. But particularly interesting about this one, minus 16.6 for that fit. So that's the same likelihood as the first signal fit, right? So for the purposes of our paper, we didn't care. It was saying with some probability it had signal. But what's super interesting about this is this is clearly a bimodal with only two parameters being moved around. This is clearly a bimodal posterior where it's just as happy with this fit, which is zero noise, as it is with that noisy fit. So this is why you have to be careful sometimes fitting these things and maybe do a bit of sampling in the low data case. So I tend to use it for that, but I was sort of there, this is the sort of shape of the posterior. So that nasty fit is all the way up there, and the other fit is down here somewhere, two modes. And they are separate modes. But in this case, I just sort of curious, what happens if you put a deep GP on it? Well, broadly speaking, nothing. Because there's nothing there, there's nothing to do. So, I mean, we're initializing in a certain way, but it's just like, it looks very much like the Gaussian process fit. So even in this very, very low data regime, we have a neural network, a deep neural network with sort of infinite hidden parameters, these hidden layers. And it's just like, yeah, it just kind of looks like a Gaussian process. And here are the inputs, sort of lots of uncertainties. That's probably slightly non-Gaussian because of in the noise. So that's not super interesting. This one, I said discontinuities could occur. In this case, I've even got an overlap between these two parts of this step function. So actually, in this case, the function, a Gaussian, I don't know. Gaussian processes hate this. I don't know why that's, so that's the Gaussian process fit, right? It's the sort of thing, they're really cross with you when you do that. Of course, in practice, and to the question before, if you knew where these things were, you would parameterize them. And you can always do that. You can parameterize non-stationarities. You can construct a covariance function. You can even fit the location of where that non-stationarity is. So even if you don't know where it is, you can be clever about fitting it, right, in a real-world analysis case. What you can't do is deal with that discontinuity in a non-parametric way. What do I mean by that? A non-parametric dealing with the discontinuities would mean that a discontinuity could happen anywhere at any time with some probability. That's the sort of thing we want our models to be able to do. You can parameterize it, but you're back to some of the challenges of a parametric model when you do that. But it's perfectly valid to do that. But here I want to go beyond that, and so this is the fit from the deep GP. So you can see, okay, here, we'll see in a moment what's actually going on here. It looks like it's returning to the mean of the function with big Gaussian noise. So you think, well, is that good or not? Here, it's sort of got, it's sort of slicing between. It's very confident in these regions. Of course, if we look at the samples, then I think you'll see those samples have just come up as actually, this model thinks it's either here or here. Of course, that could be wrong. I mean, who knows what the function does over here? But the way we've set it up, with the prior we've got, it's gone for this. And there's lots of transitions. So it believes you could transit at any time, kind of. It kind of doesn't think, there's a couple of small transitions even in these regions. It's like, well, who knows, between those points it may have dropped down. And how's it done that? Well, this is a 4-layer. To get this effect, that's probably a good thing that my laptop's going to close down in time for questions. To get this effect, all it's done is it's almost put a bunch of sigmoids together. So this is layer 1. There's 4 layers here, I think. This is layer 2, layer 3, layer 4. If I convolve, if I compose a bunch of sigmoids, I actually get a step function. And the Gaussian process is very happy to do that sort of sigmoid. It's like, that's fine. And it's injected a bit of uncertainty. I never know whether it's the way I chose to initialize these models. The uncertainty always seems to come in the early layers in these examples. I'm not saying that's going to be universal. And then it tends to seem to like to fit without uncertainty, which is interesting, right? Because, of course, that's not what's going on in deep neural networks at all, because there's no uncertainty being injected. But when I play with examples, it's very often like, I really want to use the capability of this model to mess with the error bars on the output, or to mess with that. And yeah, so this looks like a space invader, so that's the best one. You can see wherever you come in, there's lots of uncertainty here. There's still loads of uncertainty. So wherever you come in, you can actually drop either side. There's some probability. But, at at the sort of starting point, you're more likely to go on this side, and then the end point, you're more likely to go on this side. And once you've fallen into here, you might go back the other way, but it's less likely. You're sort of more likely to fall into that side. So it's a sort of pinball that splits all the balls down each side. An interesting thing about that is, this is nice. It's nice when the derivatives are like flat and then discontinuous. If your derivatives are like mostly a particular gradient and then discontinuous, the model isn't that interested in that. It's not fitting that. You'd have to do something else. This is another data set. It's called the motorcycle helmet data, which after I saw this heteroscedasticity, everyone always demonstrated in the old days when we used small data sets, heteroscedasticity on this type of data. So this is a GP fit, and what's sort of gone on is in this region here, this is a motor bicycle helmet. I don't think with someone's head in it, just the helmet perhaps. Being accelerated towards a collision, and these are accelerometer readings on the helmet. So not accelerated, constant velocity. So acceleration is 0 at the start, and then it hits, and then the accelerometers go everywhere. And there's sort of more noise. There's no noise on the accelerometers at Z0. So this is the deep GP fit, which, okay, so there are a few things about this. Check out these error bars. This again, I was complaining about them before. And maybe that's what's going wrong with their error bars too, because in some sense there's this bulk of error bar up here and nothing down here. Well, that's because, again, the true error bars underlying this are not Gaussian. They're very, as we'll see when we take the samples. And you see actually the samples stop there, dead. They stop there, dead. There's nothing above that. But they drop down into this region here with some low probability. In this region here, you're getting these sort of nice tight error bars. Not tight enough, actually, probably to what I would really want, but nice tight error bars around this bit where it's sort of totally flat. And how's it done that? Well, actually maybe that would be a better approximation if we use more layers, but it's using the same tricks again. It's mapping those points in the first region to the same point, right? With some variance. Remember, bear in mind this variance has to be fixed across here. But other than that, this is sort of broadly linear. It's basically saying, there's some mapping of these points to the same position. After that, it's broadly linear with some uncertainty. And all the uncertainty I see out there is just the uncertainty of this chirp. Like if I put uncertainty in this chirp, this moves this mode left and right, which is, of course, why we're not seeing anything above the top of that mode and lots below it. We're getting a skewed distribution. So you get all sorts of interesting effects that are like actually relatively simple to build. You're sort of giving it model all this power. You can do anything you want to model this data, and it's just gone, vaguely linear with some noise and a little bit of a flattening thing. But then, and the chirp itself it almost looks like some pure version of the original signal. Obviously, lots of things are being mapped to the same location here. This is like the time when you're in that starting point. Now, there's much more stuff that you can do with unsupervised learning, which was our first inspiration for these things. This is work by Andreas, where you're trying to model two high-dimensional figures moving together. This is before the days of autoencoders and all that sort of thing. Or digits. There's examples in the notebook where you can do unsupervised learning of digits. You can reconstruct those examples. There was a time when I think we had some of the most impressive results in reconstructing simple things like digits and stick figures. Nowadays, you see pretty impressive results from GANs and these things. I've never really understood. I don't think they can do it at low data. I don't know that. All our results are relatively low data compared to what people are doing in neural networks, up to maybe 1,000 data points. And, so in the low data regime, I think that this is all state of the art still. A lot of the challenges with these models are sort of really scaling them up to high data regime. But then this is the thing I hinted at earlier, the thing that I kind of have wanted to do for 10 years and haven't done for many reasons. We've done parts of it. Alan Saul's PhD thesis was around doing the sort of bit of this that involves survival analysis and looking at that. We've done parts of this thing, but this is trying to stitch, like, say, in health, a load of different modalities of data: genomic, epigenomic, survival, clinical, image modalities together in one model. And maybe, probably you don't want to do this for any particular application, but I believe that you could do it with this type of structure. And you could structure the interactions between these things. Well, maybe one day when we'll be able to scale these things to very large data and solve all the problems with privacy if you look at what I'm working on mainly now, a lot of it is around trying to get into a state where I would be happy getting this data, that it wasn't seriously damaging the patient's future liberties by the fact that we'd acquired this data. Because I do think the modeling frameworks, this one or others or using other things, will eventually work. And so that's it. Probably a little bit over time. Maybe one question or something. Yeah. Time for one question, maybe?
Yeah,
Did lunch arrive? Maybe someone can start taking the covers off the lunch while we do questions.
question down here.
So we've seen a lot of one-dimensional example of
Yeah.
GPSS processes. How easy is it to use them for, let's say, five-dimensional data?
Yeah, it's still a problem. You mean in initialization or?
Well, in training them, especially if you don't have a lot of data.
I don't. It depends on the approximation, but with the variational approximation, I would say it's no real issue. I only did 1D. I started doing 1D because I came up with that pinball analogy. And then I was like, oh, and I'm talking about these models and never going back to the pinball analogy. But yeah, not a major. I mean, I'm trying to think what scales with the. There's this really nice thing that while we're not using the same GP in each layer, within one layer, we're using the same GP. So that means that the statistics of the output, what tends to be, so if we think of the covariance function, what you're really caring about, and again back to what's going on in the deep GP, you've got kz1, comma z2 is the covariance function of kz1, comma z1 prime is the covariance function of a previous layer. You're talking really about the dimensionality of these, right? I mean, it's only the same issues with the regular Gaussian process. The statistics, what you're interested in is what are the statistics now of this output layer, because this is like going to Z3. Z3 is drawn from this covariance. I'm being very bad with notation here, but you get the idea. So Z3 is now dependent on the statistics of the Z2, but Z2 has this covariance. So what the interesting effect is, since Z2, we're assuming it's IID across dimensions, right? The statistics of what's happening at the next layer, in theory, don't complain too much. What can be problematic is as you start going for approximations, or you're using inducing variables, and if you're explicitly representing them, then that will scale things. So my memory is, and I'm not sure about this, things for the variation approximation I'm most familiar with, scale with D computationally. And from a modeling perspective, I think they're dealing very well with higher dimensions. But I think probably the biggest example of high dimensional input would be the ImageNet, which is not one of the things we want.
Any more questions yet?
For which scenarios are those deep Gaussian processes useful in practice right now?
All. No. No, I think where we're seeing them, and actually someone at the last year's GP Summer School asked us about this, and we've done a little bit of work on this. One of the original motivations for this type of stuff, so Javier Gonzalez, who's worked for me for, I don't know, 6 years or 5 years or something, when he came, I said, aha, and your project is going to be about Bayesian optimization for high dimensional input spaces. And our entire trick will be to project down to a lower dimensional space where we do the optimization using the deep GP, because we know GPs handle uncertainty very well. And yeah, we haven't done that yet, but someone else did it last year. And then I think there are certain areas when Bayesian optimization and in emulation, which is something we're very interested in. So emulation being where I've got surrogate modeling would be another term, where I've got a number of a more complex physical model, which isn't well approximated by a Gaussian process, where this more complex structure, I think, is very helpful. And you definitely see in Bayesian optimization things improve. I'm mentioning that example because it's a low data example, and I don't think anything else really competes in this space around low data. It's a hard question to answer what's going on in the large data regime, because it's one of those things that, doing the algorithmics, inventing a new approximation, and then having to actually implement hard code rather than just write a few things in PyTorch is quite a lot of work. And my sense is that people are so tired by the time they've done all that work that they don't really test these models properly in the way that you would want. And we, in the deep neural network community, there's a lot of people recreating results, and we just don't have that scale of community at the moment. So I think there are areas where they're going to come up, but small data is the dominant one, and for us the big interest is, as I say, emulation, things like Bayesian optimization.
In practice, Neil, how do you do structural learning in a deep GP? So setting the dimensionality.
So in fact, we had this, and it was Carl Henrik was here visiting in Sheffield with Andreas, and we were like, we want to do structural learning in the deep GP because we want to learn the whole structure, like all across these things. And we said, but the first thing we'll do, the simplest thing we can envisage is we decided that we'd look at a model that had been in Carl Henrik's thesis, which he may have talked about, or he often talks about, which was, see if I can even remember how to draw it. I can't remember how to draw it. So the model was that we wanted to combine two different data sets together. So Y1, Y2, they're related data sets. So the sort of thing that we looked at was you've got the pose of someone and the silhouette of someone. And you're trying to model it in the same latent variable model. But there's some information in the pose that's not in the silhouette, and there's some in vice versa. So you introduce what we would call private latent spaces. And it turned out to be a thing called inter-battery factor analysis that we didn't know about. And we did this all with GPs. But in those days, we didn't have this variational approximation. And so the first thing we said is, why don't we try learning this automatically? So effectively, one GP here with ARD on its inputs, and one GP here with ARD on its inputs. And they can decide which parts of the latent space. And it just works so amazingly well. Like, it was really clean. And I think it worked so well, we never really did much more than that. The intention was and has been, and I think we've even got some implementations, that you do that everywhere, that you just have ARD across the whole model and you learn these parameters. And the indication was it was working quite well. But one challenge is that, if you're starting to add all these different covariance functions, that adds to your computational headache. And the thing I said earlier about dimensionality fades away. So I think the thing that I would be interested in seeing next, and I don't know if someone's done it, I don't think they have, is just when you've got the deep GP structure, just doing the structural learning for your observation. So allowing a model, building a model that says you have a choice to construct your covariance function using ARD parameters across the different layers of the deep GP. Do you prefer to be in the lower, more detailed layers or in the upper? And I'm very curious about whether that works. I think that would be the next fun thing that you can't really do. You certainly can't do this with, I don't think you can do this with variational autoencoders. Actually, Carl, has anyone ever done that with variational autoencoders, that sort of thing?
Variational autoencoders?
That sort of, the neural network type equivalence. Has people tried that?
The shared privacy. Ryan Adams republished that paper at one point of time.
What, he reinvented it?
Yeah.
Yeah.
I reviewed it.
But did he do GPs or variation?
Yeah, so they did GPs first, and then I think people have done these things with variational autoencoder as well.
Yeah, you can imagine doing it for variational
We
autoencoder.
did them with back constraints, which is effectively
The variational autoencoder, yeah. That's true. That's true, we did. That's great. You can join the GP community and invent things that everyone ignores and then reinvents elsewhere.
You should be said that the funny comment about that model is that when we found the paper from 1958 that
Yeah.
actually introduced the paper, it has a comment that says this model is so complicated it would require an electronic computation to solve it.
It does.
It does.
We can confirm that. Probably over time, but yeah.
There was one question in the middle of.
Oh, yes.
Yeah.
So on the subject of small data, I'm aware of some recent research using a Bayesian neural network to project high-dimensional small batch data down to a latent space, and then feeding that into a GP, and then using some end-to-end optimization on the weights and the GP in tandem. And I don't really understand the maths involved. But do you have any thoughts about that approach?
Yeah, I mean, I'm just, but this would be my reply for most papers at the moment. It's like, yeah, great, and why? It's kind of obvious you can do it. I have to have a few mental mechanisms to handle this, and I think that they're good mental mechanisms, and actually they're inspired. I think the assay office is just there, right? The Sheffield's assay office is just up the street. How long have you lived here? That's disgusting.
What the hell's that assay of?
Assay office, it's where they stamp silver and the quality of silver. And so Sheffield gained its own assay office. They used to all be in London because they do so much metal work. They did do. And there's a museum. And one of the things, this is my way of dealing with things like that, which I think is, it depends what they did with it in the end, is my kind of answer, right? Because my observation of that is, this is how I reconcile those things. You're doing a PhD, and part of the PhD is to show you can do technical things. It's very similar to metalworking apprentices who are sort of going to spend a career making knives. But in their apprenticeship, they had to show that they could do technical things. So what do? They would make a very impractical knife. You know, a knife with amazing metalwork. You would never want it to use it for cutting anything. But anyone who understands the technical skill required would go, yes, this person has learned the technical skill. And I don't know what the percentage is now, but I'm just feeling that certainly in the community at the moment, and it's a totally valid thing because we need a generation of people who know technical stuff, but 95% of the things are impractical knives with lots of technical things. That one is, that idea is something people, have known about, talked about. You can certainly include anything you like in your covariance function, any mapping. So make it parameterized neural network, whatever you like. The question to me always has to be, why are you doing it? And if it's, because I think that this will get published, that's fine, because that seems to be mostly why we're doing these things. But I only become really interested when you have a really interesting reason why. So the sort of reason I think you want to do that type of thing is because you've maybe got an image as your input and you want to build convolutional filters on the image.
And you have very few of them.
Yeah, and you have very few. And there's then the interesting question to analyze is, how much benefit are you getting in terms of data efficiency? We did a lot of work on that at Amazon, and the depressing answer was not a lot. I mean, like some, but not so much that you couldn't pay for another double your data set size and you're probably there, which is not good enough. You need to be an order of magnitude better, I would say, at least. Carl, you had a...
Yeah, just to comment on those things. The really tricky thing about doing that, when you're mixing those two things, is that the uncertainty is completely different, right? And when you try and propagate it through the models, because they effectively mean completely different things, right? If a database neural network is you trying to reinterpret an uncertainty in parameters to be about data, and then if you put the DT on that, like, they don't mix. So what often happens in practice when you try and train these things as well is that they don't want to match at all. So, for example, there was a paper last year by Niccolo Fusi, who's a fantastic person, where they had a VAE and a DP, which sounds like a great idea to overcome lots of the problems of those models. And it sounds very nice, and I've tried this as well. And then there's a comment saying, well, the best way of training them is training one and then training the other on top of it. Because if you train them jointly, they're both just going to say, this is effectively exactly what happens. The GP is going to say, well, you know what? I can go to a space where you don't need me anymore, and then I can just do my thing over here. I'll just fit the trier, and I'll be super happy, and then you just train a normal VA. And that's exactly what, in most cases, what happens. And you try to do these concrete dropouts and all these weird hacks to propagate this, and that it simply doesn't work because it's wrong.
And there's this, I think it's one of the depressing things about uncertainty is that you're told this promise that you can do that sort of thing. And, another area where that would be true is like language modeling, people not training versus phoneme modeling in HMMs. Of course, those days have gone. Yeah, you have to be really, probably end-to-end training with uncertainty is quite hard as well. Yeah, that's true. Should we get some lunch?
Well, let's leave it there. We're going to have lunch now, and we'll start the lab sessions at 1:45.